What's up, friends and frenemies? We are on lesson 3 of unit 5 of Algebra 2. We're continuing our discussion of polynomials. In this lesson, we're going to kind of get into some graphing. We're going to talk about polynomial functions. We're going to, my goodness, it's the wintertime, dry air, all the things. We're going to talk about a handful of concepts, do a couple examples, and then we're going to be through. And the first concepts we're going to talk about is the degree and the leading coefficient. Okay, so I color coded this already, so you can kind of just look at it and probably be able to tell me what we're talking about. But in case you can't, let's talk about it. So the degree of a polynomial function. Oh, that's funny. That's funny. That if anybody knows what we're talking about, I actually accidentally colored this backwards. I'm going to change this live on camera, except not live. Wow, how could I do that? Oh my goodness. All right, so that color, sure, that's fine. So the degree should have been yellow. So the degree of a polynomial, we've kind of sort of talked about this before. But to make it official in our notes, the degree of a polynomial is the number of our largest exponents. So like this one right here, his degree would be 0, right? The degree of this polynomial function would be 0. 0 degree. Right? The leading coefficient of the polynomial, let's add that back in here, leading coefficient. In T. All right, we did it. We got it. Yay. Okay, so the leading coefficient is the number that's in front of the term that contains the degree thing, right? So this right here the leading coefficient would be 12. Now this one's a different type of a thing, right? So it's leading coefficient. I'm going to do Ledkoff abbreviated with a nice little period there so we can, whatever. So our leading coefficient on this one would be 8, right? Now, this guy, if it's just, doesn't have any letters, he has a special name. The special name for him is a constant function, right? So now this example here, what is his leading coefficient? His degree is 1. He has a degree of 1. So, because remember, if there's nothing there, it's a 1. His leading coefficient is a 3, right? This guy, in this one, what is it called? This one you probably know. What is it called? If we just have an x to the first, this is called a linear function, right? We knew that already. This one, the degree would be 2. This is a second degree polynomial. It's also a quadratic, right? We know that from the last unit. Quadratic. I don't want to put a period on it. Anyway, quadratic. And this particular quadratic has a leading coefficient of 7. The leading coefficient on these doesn't always have to be positive, right? I just put that here. This one here is a cubic function. A fourth degree polynomial would be a quartic, I think, and a fifth would be a quintic, and then I don't even know, right? Something, right? So the degree on this one would be 3, and the leading coefficient would be 12. This guy is just a generic. We're going to go and label him, right? So whatever number is in front of this very first term when the thing is written in descending order is the leading coefficient. So the leading coefficient in this generic case is kind of sort of like a series notation, sort of, kind of. Some of you may learn more about that in the future. Some of you may not. That should be an n, a sub n. And the leading coefficient in this generic one is n, right? So let's take a look at some examples real quick. So we're going to state the degree and leading coefficient of each of these polynomials in one variable. If it's not a polynomial in one variable, we're going to explain why, right? So this one right here, what is his degree? His degree is 5, right? 5 is the highest exponent. What is his leading coefficient? His leading coefficient is an 8. There's number 2. This one is not a polynomial in one variable. Not a polynomial in one variable. But why is it not? Well, because it's got 2 variables. Not a polynomial in one variable. Because x and y, right? This one's a little sneaky. Did you notice? So this one, so in order to figure out what the degree and the leading coefficient is, it has to be written in descending order. It isn't written in descending order because this one would have to be moved over there. And so it would be negative 4x to the 8th plus 3x to the 4th, etc., etc., etc. So this one is a little bit sneaky. So this one is an 8th degree polynomial. It's an 8th degree polynomial. That's the highest exponent. And the number in front of that is a negative 4. So the leading coefficient is a negative 4. Right? Easy peasy. Let's do another thing. All right, we're gonna kind of sneak this in here. This kind of sort of fits in this lesson and kind of sort of doesn't. This is kind of a function notation on steroids. Whenever we've got a function notation expression that we've got to take care of, and so we're gonna kind of sneak this in here. So we're gonna find f of 3c minus 4 minus 5 times f of c if f of x, so this is our original, our OG polynomial function, right? And we want to find all of this. So we've learned how to do this before. We've learned how to do compositions of functions. We've not really done it in this big old thing. So we're going to kind of do this. Let me kind of do some different colors here. We're going to do this little chunk separately from this little chunk. And then we're going to kind of put them together at the end. So let's first find f of 3c minus 4. Right? So remember what we do is we write our original function with parentheses where the variable was, where that x is. It's a function of x. So replacing x with that plus 2 times and minus 3. And then we're going to take and plug in this everywhere where the x was. So 3c minus 4 and then 3c minus 4, right? Now we've got some things to do. We've got to distribute this one. This one, we've got to FOIL this. We've got to factor it out. I'm not going to use the FOIL shortcut. I'm going to do it all the way out. I may kind of add me another little space. So I'm going to do 3c minus 4 times 3c minus 4 because that's squaring it, right? We did learn a shortcut. You're welcome to use that shortcut on your work and whatever else, but I'm going to walk it all the way out just for increased clarity. So 3c times 3c, 3c times negative 4 times 3c, negative 4 times negative 4. So 3c times 3c is 9c squared. 3c times negative 4 is negative 12c. Negative 4 times 3c is negative 12c. And then negative 4 times negative 4 is plus 16. We've got a couple like terms. So this ends up being, I'll go ahead and bring it back over here, 9c squared minus 24c. Excuse me. And then this one, we're going to distribute this. So plus 6c, because 2 times 3c is 6c. 2 times negative 4 is negative 8. And then bring down my minus 3. Do I have any like terms? Sure as shooting I do. I've got that one with that one and this one with that one. Right? So this one turns into, so f of 3c minus 4 turns into 9c squared minus 18c minus 11. Does that look right? I think so, right? So that's this first bit. Now this negative bit, this next bit, we could actually do the negative 5. I'm going to deal with the negative in a second because I think that's going to be easier to see what we're doing. So this next bit, we're going to do 5 times c, 5 times c. 5 times f of c. So 5 f of c, f of c, so we're changing our variable to a c, and we're multiplying 5 times it. So this, we're going to multiply 5 times the whole function, replacing x with c. So this is going to be 5 times this whole thing, but with c in for x, squared plus 2 times c minus 3. Now, you can see what we're going to do, right? We're going to distribute that 5. Distribute the 5, distribute the 5, all the things, right? So that equals 5, this is 5 f of c. C squared plus 5 times 2c is 10c. 5 times negative 3 is negative 15, right? So now what we want to do is we want to take this pink one, this guy, and minus that guy. And so that's exactly what we're going to do. Let's change this over here. We'll go back to a white, I think is fine. So we're going to say, let me kind of, f of 3c minus 4 minus 5 times f of c is going to be this first bit. So this one equals 9c squared minus 18c minus 11 minus this one, so that guy, minus 5c squared plus 10c minus 15. So what do we got to do here? We got minus and then all this stuff. I did that in parentheses. I did that on purpose. We're doing minus this whole schmagoigle. So minus all this thing, right? So we got to make sure and do that. Otherwise, you're going to make a mistake on the negative because, I don't know if you saw this here or not yet, but we've got to distribute this negative, right? So we got to do that before we can do anything else. I'm going to kind of schmooth this over a little bit. 9c squared minus 18c minus 11 minus 5c squared. Distribute the negative, so minus 10c plus, because negative times a negative is a positive, so plus 15. Do I have like terms? Sure as shooting. So this one and this one and these away, that away, whoop. And then finally, this one, right? So 9c squared 9c squared equals 9c squared. But 9c squared minus 5c squared is 4c squared. Negative 18c minus 10c is negative 28c. And then negative 11 plus 15 is plus 4. So there, better make that 4 a proper 4 and not a 9 wannabe. There we go. Okay, couple more things, and then we're through. So, end behavior. Oh no, a big thing. So, end behavior, what are we talking about here? What is this concept? So, what are we talking? We're talking about what happens at the ends, right? At the ends of these polynomial functions. So, we're talking about, and we've got kind of a new symbol here. This arrow in this context means approaches. This is approaches. Okay. So in this first one, that it has an even degree. Now we already saw that this could be like that, right? Or whatever, right? It's an even degree function that has a positive leading coefficient. So what all this means and what's happening here is as x approaches positive infinity. So as x is getting bigger and bigger, the f of x, the y, is going up. That's this one here, right? Now, as x approaches negative infinity, y, f of x, the function, is going up as well. So you notice that the f of x, the function itself, on an even function, on both even ones, they go in the same way. Now, so the way I have described this in the past, I've used, like hand motions or whatever. It's kind of hard, you can't really fit in the screen, but even degreed functions look like this or like this. It's hard to do. Usually I'm like this, but like, close enough. It's hard to do this like I normally do in person on camera, but even degreed functions open in the same direction, right? Up or down, right? Same direction. Odd degreed function, I'll go back to the picture here in a second. Odd degreed functions open like this. It's hard, you do the walk like an Egyptian thing. This or this. Just doesn't work as well. Like that. This. Close enough. Let's go back to picture. Right? So even degreed function, either both sides open up, or both open down, right? So on this one, if it's even, but the leading coefficient is negative, as x approaches negative infinity, so as it goes this way, the function goes down. It approaches negative infinity, right? On this one, as x approaches positive infinity, the function is going down, right? Now, I should note a little side note on even and odd functions. You are liable to, in pre-cal or in college algebra, learn that this is not quite always true, and there's kind of exceptions, and there's other ways to look at this. But for our purposes right now, this is perfect, and this gets us there. So on an odd degree function that the leading coefficient is positive, I should, what would be actually kind of helpful? Let me add this little thing here. So example of what this would be is something like f of x equals 2x squared minus 6. Now, that's not this function, but something like this. This one would be something like, this guy down here would be something like f of x, what is happening? F of x equals negative 2x to the 4th. Right? So negative leading coefficient, even degree. This guy, if we have an odd leading coefficient, so something like f of x equals positive leading coefficient, so positive 8x cubed. Right? Something like that. Right? If we have a odd degree and a positive leading coefficient, as x approaches negative infinity, so as we're getting lower, the function is going down. It's approaching negative infinity. This guy, as x approaches positive infinity, so as it goes to the right, x is approaching or heading towards positive infinity, so it's going up, right? Now, for an odd degree negative function, so something like f of x equals negative x to the 5th, right? Something like that, right? odd degree, negative leading coefficient. As x approaches negative infinity, so as x is getting lower, as we're going to the left, the function is getting bigger, so it's approaching positive infinity. So as x approaches positive infinity, so as we go to the right, the graph is approaching or heading towards negative infinity, right? So that's how end behavior works. We got one more thing to talk about, and then we're through, right? So zeros of odd and even functions. This is another thing where there's actually technically kind of exceptions to this, but that means something specific. You'll probably get more in a pre-cal or college algebra class, but for right now, this is good enough for us. Odd degree functions will always have an odd number of real zeros. Now, what were zeros, right? We had that before. Zeros are where the function crosses the x-axis. So, like, we're talking about this one and this one and that one and that one and that one, etc., right? Wherever the graph, the function crosses the x-axis. Those are zeros. So an odd degree function will always have an odd number of real zeros. So pause. So how many zeros does this one have? It has 0 zeros. It ain't got none, so it doesn't ever cross the x-axis. How many zeros does this one have? 1, 2, 3, 4. That's 4 is an even number. So this is not an odd degree function, right? 1 is an odd degree function, so this one is odd. Right? 1, 2, 3. 3 is odd, so this is an odd degree function. Let's finish reading our sentences here. Even degree functions will always have an even number of zeros or no zeros. This one has no zeros, so it is even. This one we already counted had 4 zeros, so this one is even degree function. And that's it for this lesson. That's the notes. That's some examples. See you in class. If you're one of my students, I will see you next year. If you're not one of my students, thank you for joining us. Hope this has been helpful to you. Let us know how else we can help you with math, science, or homeschooling in general in the comments below. Have a great and wonderful day. Bye-bye.